Good afternoon, everyone. Thank you for coming. We're very, very excited about the Piedmont Student Launch Team's one book discussion today. And so I would first like to introduce you to our panel of speakers. We have Andrew Oxford, Daniel Hall, and Rodney Davis. And they're going to be speaking about their experience of working with NASA engineers on a 9-month-long research-based competitive exploration project of building and launching a high-power rocket with an experiential payload. I will let them talk more about that. I'm very excited to hear about it, so I will turn it over to Andrew.
Thank you. So to start with, I want to go over real quick just what the project is for people who don't already know. It's a project that So it's a project that NASA does each year where teams from around the country come together to build a high-power rocket and a payload. You come together to design, build, and test your rocket and payload throughout the year. And it's an 8-month project, and there were about 60 teams last year that competed from all sorts of schools around the country. There was Vanderbilt, Cornell, U.S. Naval Academy, and a whole bunch of other really big schools doing this. There were 2 other community colleges in the entire country doing it, one from California, one from Florida. So we're the only actual really small school and community college doing this, or at least one of the few, the only one from Virginia, which was pretty fun. There are, as I said, it's 8 months. There are different different challenges that they do each year, which Daniel can tell you a bit more about once we get to that part. But there were 3 different options for what challenge you did last year. You can see our payload that we used down over there. Which was the roll control challenge. They also had ones for target identification and vertical landing, and one that was fragile payload protection, which basically amounts to a glorified egg drop where you shoot the egg to a mile up and try not to break it. For the design part, first you create an initial design, of course. There are 3 iterations of that go to NASA throughout the project, and each time you get feedback from them about ways you can improve it, and also making sure that you meet all of their requirements and that it's safe and you're not going to land a rocket on someone. And each time as you improve your design, you also then go to building more and more complex parts or complex iterations of your design and testing those. There's a subscale rocket that you end up building. This here is our full-scale rocket, which is what we flew down actually in Alabama, but there's a subscale rocket that you build earlier to test your airframe, and you do that after your second design iteration. This you do after the final iteration, and prior to that first rocket, you can of course build things just to test out parts of your design. So we don't have the subscale here because we used it for a lot of testing, and it is not exactly in presentable condition anymore. If you ever see it, just ignore the mud that's epoxied on now. So the whole project is modeled after the federal contracting process. Which is really what actually makes this project the most work. At the beginning, there's a request for proposal that NASA sends out. You write a proposal to them with what's your first design iteration. After that, if you're accepted into the project, which is a competitive process, your proposal has to actually be accepted before you're in the project. There were 60 teams accepted last year, of which we were one. So after that, you have several design reviews. The first 2 are where you actually send in your next 2 iterations of your design. The third one is where they actually show that your design, or show that this final rocket actually works properly. That's after you've tested this. And then there's one at the very end of the project where you actually review what you did and if this worked in Huntsville or not. So that is by far the biggest, the largest amount of work in the project. You have to write a report for each of those designs. The shortest well, the shortest report was about 15 pages. That was the very last one. Other than that, the shortest report was over 90 pages, and the longest was about 150, which is actually smaller than a lot of schools. They went right up to the limits that NASA allowed and did like 250 to 300 page reports. And on top of that, 3 of those include a presentation to NASA. It's done by teleconference, and every team does one to actually directly tell them, what your design is, all your analysis, and all the testing that you've done, and things like that. And it's where they ask you questions about your design. And then the big, actually exciting part of the project is the final culmination in Huntsville, Alabama. It's what's called Launch Week, where all the teams go down, gather in Huntsville, Alabama, and Daniel will tell you about it in a bit more detail, but basically that's where they do the final check of your rocket to make sure it is definitely safe. It's not going to fall apart in flight or anything like that, and then you launch it and actually see how it works. Also, they feed you, which is really nice, at least on the last day. So now we're going to go over what we actually did in the project real quick. I'll start by handing it off to Rodney to tell you about our actual rockets, both this one and the subscale that we built earlier in the project.
What's up, everyone? I'm going to stand up because I don't want to keep turning around. Yeah. Oh, sorry. No. I don't work too well with microphones. So basically, as you can see, this is our launch vehicle right here. This is a picture of our subscale where we tested all of our experiments on. It was significantly smaller than our full scale, which is right here. And we just did the subscale to test the principles of what we were trying to prove to NASA, because we also had to put testing and analysis reports in what we sent them, because you don't want to launch something and like blow up in midair. And as Andrew had pointed out, it's kind of muddy right now and just kind of strewn about. So the subscale was 6 feet tall, and we chose that height. Well, technically because like we didn't want to like go all out and build a full one, and so it's much easier to keep keep retesting the same concepts on a smaller scale rocket, and cost reasons and all that good stuff. It's 4 inches in diameter versus our 5.5 inches, 12 versus 37, and 73% scale versus our which is almost 9 feet, 9.5 feet. Yeah, so see the difference there if you have a knack for numbers. So basically, this is made of fiberglass, and sanding it and getting it all like worked out was kind of obnoxious, to be honest with you. But the fact that we were able to do it with our hands was kind of cool. I remember Andrew here gave me a fin and told me to sand it down. He's like, sand this. I'm just sitting there like, oh, this sucks. But I was like, oh, this really sucks. And we had, obviously wear protective PPE. Me being the, obnoxious one, I was in the workshop with sandals because, done the whole welding thing. So I was just like, I know what I'm doing. But I probably won't do that again. So yeah, we basically made everything by hand, and it was quite an experience, to be honest. Like, to watch it go up after building it by hand, it's like seeing your little kid go off to school for the first time. Like, okay, go have fun, don't hurt anybody, don't hurt yourself, that type of thing.
So for the payload that we chose for the rocket, we had a couple different challenges that we were trying to meet during the project. One of the specific ones that we spent a lot of time towards was a roll, induction, and dampening challenge. So the idea was to create an instrument that would live within the rocket that would be able to control the rocket's rolls as it was ascending and descending. And we did that with our payload we have at the end of the table here. So using that, we were able to compete in this challenge, and we used a 1.5 pound reaction wheel. So if you look at this thing, it's pretty much just a large wheel that we filled completely with bolts to act as a weight. And the idea is that by spinning it, we're able to go and provide a rotational force that counteracts the rocket's own spin, which allows us to control all the roll when it's in flight. So part of this project had a lot to do with the deliverables and the timeline that we had to work along. Since 8 months goes by a lot faster than it seems like it would, we had proposals we had to do. We had a preliminary design review, the critical design review, a final design review, and the PLAR, which I cannot remember the acronym. Right. So all of these were long, arduous tasks of hundreds, like dozens of pages just for each individual section describing exactly what we were going to do, how we were going to do it, really thoroughly capturing the federal contracting process of everything needs to be documented, everything that might be a problem needs to be documented, and even if we don't think it's going to be a problem, if there's a chance that it could go wrong, someone needs to know about it. So we also had to do multiple presentations. Part of it was our community engagement that we did throughout the year. Part of it was also to help get the word out about STEM in our community. And additionally, presentations we had to do to NASA engineers in order to be able to sell our product almost, to be able to say, this project, we know that we believe it will work. We have confidence in the ideas that we're trying to do, and then they would give us feedback based on that. And additionally, we had several launches over these over 8 months. Most of them were in the local area. Some of them were at Battle Park. A couple, I want to say like 20 miles up north-ish. I'm bad at maps. But we had multiple launches in the dead of winter. It was never nice weather when we were launching. Some of the launches wound up in failure, but it was definitely the failures that helped us get a much more sound final product out of the whole project. And additionally, all this was working to a project plan that was created by Andrew. This helped us keep an orderly timeline of documentations and deliverables to make sure that we had everything completed by the time that it was needed for the project, which was immensely helpful, especially when you're working to hard deadlines with time.
And if you want a fun thing to try doing just for fun, try managing like half a dozen community college students' schedules.
Especially me. I'm the most obnoxious one. And I do it just to go to yours. I love you.
I assume so.
Okay, cool. So for educational engagement, throughout the year, part of the project's requirements is that you need to have a specific educational impact on your community, which over the year they want you to have at minimum 200 people that you're interacting with. We made it our personal goal to aim for much higher than that. So we held several events over the year. We had Girls Geek Day, where we went out to local public schools and held STEM-related events to be able to teach females about different areas of STEM that they might be interested in, to try to drum up support for science, engineering, and technology. Additionally, we also held the Family Space Exploration event, which we had here. Which was a full-day outing for people to get interested in rocketry, as well as different science and engineering activities for families of all ages. And when we were done, we were able to exceed the minimum community engagement by nearly 250%, which we're hoping to get even more community engagement for this coming year. With the Launch Week was held in Huntsville, Alabama, after all 8 months of the project. There we had to give our launch readiness reviews to prove that everything we'd been working on for the past few months was that the engineering was sound, and that the NASA engineers in charge of the event could reliably understand that our project was very likely going to work, and that we didn't pose any kind of serious risk to any kind of safety. Additionally, we were also given tours of Marshall Space Flight Center. If you ever get the chance, just any of the NASA centers are just really cool, since none of them do the same thing. So Marshall's had a lot. They held a lot more of the historical rockets that were really big when we were doing the first space race, which you can't find except for maybe a few other facilities. And finally, we had the Rocket Fair, where all the competing teams were held together, and we were able to present our rocket to anyone that was interested in the event, as well as we were able to check out a lot of other teams' rockets, which we got a lot of ideas from that. Other people got ideas from our work. It's probably one of the best cases of just being able to really learn from the other teams that are a part of the experience, which very helpful for this year. So for launch day, launch day was, we all had to get up at, I want to say about 4:30 in the morning to be out in this just empty, dark field at 5 in the morning. And past that, it was a full-day event to be able to get our rocket prepared, get everything set up in preparation for the final flight for the contest. This was the flight which they would wind up going and scoring for our final score for the project. So, and this is where they were going and looking at the different challenges. So, of the challenges they were looking at for launch day, they were looking at an altitude challenge, where the goal is to have your rocket fly up exactly 1 mile off the ground. You can't go too high, you can't go too low, and I want to say that the team that got the closest to it, they were within 10 feet of that goal, except that they apparently also broke Mach 1, which was not allowed, but very, very interesting. Huh? I'm bad at names. Toledo, yeah. And additionally, we also had our roll induction challenge, which we competed in. And there were some other challenges as well, which included a target identification challenge and the vertical landing challenge. So overall, it was a long day. Most everyone got sunburned after that, but it was just truly incredible with the amount of success and the results of the project. Yeah, and we had almost vertical landing, which no one else really cared about, but that's really, really good for just regular rocketry.
Also, we should work for that. But,
Yeah.
Closest to the Launchpad. Yeah, it literally was.
Yeah. So we have a video here this is a live video that we took from our rocket on launch day. Yeah, so you can see that it's spinning. It starts spinning off pretty quickly, and then it starts slowing down due to the reaction wheel built into the rocket. So our final altitude for the flight was 5,500 feet, which it's a little bit off from a mile, but it's still really, really close considering all the factors that were at play. So this part gets me every time, since I mostly I spent a lot of time doing the parachutes. So this part gives me a heart attack thinking that I could have screwed that up.
Makes me
Yeah. Yeah, so what's happening right here is the rocket has 2 parachutes built into it. One of them, which is the drogue parachute, it's that small orange parachute there, which it's mostly to be able to get the rocket out of terminal velocity. And then you're basically relying on that to slow it down until about the last 500, 600 feet. And then you deploy the final parachute right there. Since if you deploy the parachute at the maximum altitude, it's going to go sailing for 4,500 feet with maybe 20-mile-an-hour winds. You're never going to see that rocket again, ever. So it's definitely a balancing act to make sure that you can recover the rocket as well as but you also know that you're not using too large of a parachute that you rip the rocket apart.
And when you said we stopped the landing earlier, that's because the nose cone stopped in the ground. That's why you can still see the sky there.
Oh, yeah.
You literally stopped the landing.
And I'll pass this over back to Andrew.
So that's all that we actually had to present about. So I guess now we're on to the Q&A bit. So if you have questions, now is the time.
I'm not too fond of rocketry. I'm not interested in it. I'm sorry. But are you guys able to compete with more than just one flight challenge?
Technically, yes, you are allowed to do multiple challenges, and we actually sort of tried doing that. with this rocket, we combined the roll control with routing. Can you hold up the camera on there? So we were trying to combine that using this camera with the target identification challenge, which didn't work perfectly, but you certainly can do that. And there were a lot of other teams that did also do multiple challenges. This year, actually, there's a chat channel that a lot of the team leaders are on, and someone posted a poll to see who's doing what challenges this year. And it looks like there are several teams that are doing all of the challenges. Most of them are only doing one or two, though. Anyone else? Yeah.
Tell me about the painting on the rocket, what that symbolizes and means.
I don't know that it symbolizes much of anything, but so we went with a Lord of the Rings theme for this. We've got the upside down one ring over here, Smaug pointing that way, which looks fairly cool when you actually launch because you've got the mouth going down there, and then we used a motor that has a red flame, so you get the fire coming out the back. This is the name of the rocket, which is actually in Elvish. I think it's Quenya. I don't remember exactly. It's either that or Sindrin, one of the two. And then I think it says the name in English down here somewhere. And then, yeah, so we actually had someone come in to do the painting because we're all engineers and we suck at painting. But the person we got is pretty good. So there's actually a competition for best looking rocket as well, which unfortunately we didn't win. I think that's mostly because our rocket wasn't like up above everything where everyone could clearly see it when the voting happened. Because the team that did win, it was a pretty basic paint job, but their rocket was really tall, so everyone could see it.
I actually went around the fair, like, trying to, like, get people to vote. I was like, hey, man, vote for a rocket. Rudy was like, PVCC. What's that? European Community College. I've never heard of it. All right, look, I know your birthday, and I get that, but, like, vote for a rocket.
I was just gonna ask, what are the next steps in the launch team? What's the next project?
So we're competing in student launch again this year. The proposal or the request for proposal this year came out about I think 3 weeks ago, as of today or tomorrow, and the proposals are due to NASA a week from today. So we are currently in the process of writing that, and then we actually really get into the challenge. This year, the payload challenge is, at least the one that we chose, is to build a rover that sits in the rocket, and then once it lands, you actually deploy that, and it has to drive away a bit and open up some solar panels. So it should look even cooler than that one.
I just want to point out that the proposal process really sucks because you have to like really like, and I use that word lightly, but like you have to like kind of just like
Stay on top of it.
yes, in which Dan can tell you I'm not best at that.
Yeah, it sucks less when your team members get their parts done on time.
It's long, it's arduous, but it's also a really effective life skill if you're getting into these engineering fields. Since being able to write these kind of documentations is something that employers are looking for, like, today.
And even if you head to grad school, writing a proposal for that stuff is amazing quality. I can't tell you how many grad students I've met who can't do a proposal, or they run to their advisors like, hey man, can you look over this for me? And they're like, dude, like you spelled cat wrong. Just like, because they got so much research to do, and they're just like nailing away at these proposals. And yeah, a lot of research money comes out of government grants, so this is a good like skill to have on top of it.
So we've got a question back here.
David asked about the next step for the rocket team. What's the next step for the three of you after PVCC?
Well, I'm planning to go on to UVA and do aerospace engineering there, then probably SpaceX. And I will hand that to you so you can talk.
Yep. Well, personally, I'm doing a guaranteed transfer after this year to Virginia Tech's engineering to do mechanical engineering with an emphasis in robotics.
I probably head off to VCU and do chemical engineering and co-op with Chemours Specialty Chemical Company, and from there start my own business. If I don't get into VCU, I'll just see what happens from there. But enjoying the ride, man. That's it.
You have a question? Does NASA help provide funding for you guys to do this, or is this something you have to do fundraisers?
We do have to do our own funding for this. The school has actually given us a fair bit of money, but it's a moderately expensive process. You have to, of course, build the 2 rockets, your payloads, all your test equipment. You have to pay for lodging down in Huntsville, which luckily NASA does get us a discounted rate, but we do still have to pay for it. Unfortunately.
Corporate sponsors, or see Tiger Fuel, hats, or the sponsors.
Yeah, so they were one of our big sponsors last year. They also let us use their conference room for doing our teleconferences.
Yeah, put their logo on your rocket like a NASA.
Last year, I think we wore these hats to symbolize.
We seriously considered laser etching our sponsors' logos into the fins. But
So you create an entirely new rocket from scratch every year, and how do you control for the height? You guys change the weight of the rocket, or you guys create your own engines to meet that height challenge?
So for the building the rocket each year, we at least are planning to do a different rocket each year and completely scratch built. There are teams that reuse their rocket year to year, but we think we can actually improve on the design a little bit. Turns out those kinds of fins really suck because they can break fairly easily. But and as for the altitude, we're actually not allowed to make our own fuel. We have to use a commercially available motor, which unfortunately we don't have with us today, but it's about yay big. It weighs something like 8 pounds when it's full. So we just, in this one anyway, we just chose a motor that got our rocket pretty close to the altitude we were going for and then adjusted the weight to get it closer. This year we're actually at least looking at doing an active control system like air brakes to provide drag so that we put a motor in that will actually shoot us over the target altitude, but then put a control system that will increase our drag so we bring the altitude back down to what we're going for. And that way it helps control for variability on the day of the launch, like just temperature changes things and each motor is a little bit different. So.
And for somebody looking to join a club, what type of time commitment would you say you guys had last year?
So last year, really, really high. It's looking to be a little lower this year because we have a larger team. It's more than twice the people we had. I think we're getting close to 3 times as many. But probably I would commit about the same time you would for a full class for this, just because there's a lot of work involved in the writing and the design and building, testing, all of that, plus the occasional weekends to go out and actually launch them, which
So you consider it a writing intensive course with a payoff?
only a lot more writing than an actual writing intensive course.
Where did y'all place in the competition?
Unfortunately, we don't actually know because they don't post all the scores. They just post, I think, the top 3. But I think we were, from the scores that we did get to see for each of our documents and all of our other parts, it looks like we were at least pretty good in there, pretty high up, which I think particularly for a rookie team was pretty good. There were other teams that had been in the project before that didn't do so well. There were 60 teams at the beginning of the project and only 52 by the end, so we beat both Vanderbilt and Naval Academy for the altitude challenge. I think we beat them by about 1,000 feet for that. So we may not have won, but we did pretty well, and we're hoping to do better this year.
So, who designed your rocket? Like, I know there's probably there's like a lot of math and physics behind it.
So, we all just did the design. There's actually, at least at this scale, there's actually less math than you would expect for it, just because there are a lot of programs out there where you can put in your design and model what will happen. So you actually just really edit it in that. But so it's a fairly straightforward process, but there is definitely a fair bit of that involved. And particularly with the payload, that's where you really get into the actual math and physics, because that you have to design entirely by yourself. You're not going off of, the pre-existing basic rocket design.
It's not like a research project where you like you can't like Google this and like copy paste. It's like more like you gotta like literally like figure it out. Like it's really really hard. Like for our design for our rocket design this year, we pretty much like for lack of a better term argued with each other at one of the meetings, and then we hashed out what we were going to do. And you throw ideas out there. You're like, what about this? What about that? And like, it's dumb, but you say it anyway, just because. Why not? And then someone would be like, oh, well, that won't work. And you're like, okay, well, that makes sense. And then you get like different perspectives from like every arena. Like Andrew being Aero, Daniel here being Mechie, me being Chemi. Like it's just a lot of like different perspectives, and we all come at it from a different angle, which is really cool. Chemi doesn't really fit much into this, but I don't know. I've fit in pretty well.
Start using your own fuel.
Yeah. Let's not talk about that.
Yeah, so on the note of dumb ideas that people have thrown out, 12 fins, not a good idea. It's a lot of fin fillets to sand.
I just want to look cool, man.
Anyone else?
I have a question. Can you describe what is that again?
Oh, yeah, so this was the payload experiment.
Yes. Can you describe what's happening here?
Right. So this was the reaction wheel, which was our main payload, which we used for the roll induction challenge. And yeah, so the electronics on here are to be able to control the rotation of this weighted end here, which is 1.5 pounds of just like steel bolts.
32 steel bolts.
32 steel bolts.
Each with 3 nuts.
Yeah, so relatively heavy compared to the rest of the rocket. And the idea is that by spinning this, you're able to change the roll of the rocket while it's in flight, and you're able to use this. And that was one of the challenges, was to be able to create some kind of instrument to be able to control the rocket. We didn't have to do specifically this design. There were some teams that did it with like external fins on the rocket, or I think there was one that tried doing it with air.
Yeah, Vanderbilt actually tried doing it with compressed gas thrusters. I think it was CO2 based. So they had little thrusters sticking out the sides of the rocket that would control the spin.
That was really my idea. Like, that was so cool, man. Awesome with that beat.
Yeah, so I can flip it around. Flip it around this way. No, this way. Yep. So for electronics on here, we've got this is our transceiver, so that we can actually communicate with this while it's in flight, which is really important because there's a GPS there, and we are actually specifically required to have a GPS location on the rocket at all times. So that's a very important part. There's an IMU down here, which gives us, that's what we use to actually measure the roll of the rocket. Inertial measurement unit, or something like that. I never remember what it means. What else do we have? So we have the Raspberry Pi, which actually is what controls all of that. The batteries are on the back. There may be electronics here that I'm forgetting. No, there aren't. Okay. We've got a motor controller down here, which is what actually controls the motor. We have a mishmash of batteries. We've got, there's supposed to be 2 9-volt batteries here. There's only one right now. This has some AA batteries, which I don't actually remember what powers what, because that wasn't my job, but the person whose job it is isn't here. You can also see, kind of fun, we have these nuts epoxied onto the sled here just to keep the batteries from shifting about.
There's no holes attaching this anyway. This is just epoxy.
Yeah, those batteries were a somewhat last-minute addition, just to make sure we could actually power everything. So, Yep. You can also see our very high-tech solution on there for pulling it out of the rocket, the string. It's harder than you would think.
Andrew, if anyone is interested in joining the team, perhaps, can they give you their emails today, and we would include them on in communications?
They certainly can. So you can also email info@piedmontlaunch.org, and I will get any questions that you have there if you're interested in joining.
With the design process, now with NASCAR, you have to have stuff within a certain measurement and whatnot. Is it that way with your challenge in the rocket, or is it just whatever you can fit into to meet the challenge requirements?
It's kind of a mix of the two. There are a few specific dimensions and values that we actually have to meet, but there are very few of those, particularly for the payload. There's 3 requirements for the payload, and that's just about what it actually has to do, not how it has to do it. A large part of this project for NASA is to get people to actually innovate in their designs, so they keep the actual requirements to pretty much a bare minimum, and whatever you can do, as long as you can do it safely, they'll let you do. They do, however, frown on blowing up the rocket. You're not allowed to do that on purpose.
It was pretty interesting down in Alabama to see the different schools and how they did things. One school had a really, really tall, thin rocket. Who was that? Was that Oregon? Oh, Toledo. Okay. Yeah, I can't. I don't know. Anyway, but it was really tall and really thin, and it was just interesting to see how different schools did different things. And I was talking to a few of them, and for a few of them, it was their capstone project because they were graduating and they were heading out. And I went over to Berkeley, and I was like, man, you guys are the best engineering school in the world. I was hyping them, I love Berkeley. And I saw the rocket, and I was like, wow, you guys really dropped the ball on this one, didn't you? Wow, that's interesting. Wow. And then you saw a couple schools. The Naval Academy, that one was really interesting to see what they did. Through a grapevine, I heard that they had a big budget, really big budget. Naval Academy, blah blah. And a lot of guys were majoring in aeronautic engineering, and they're heading off to the Navy or going into the corporate world. And I went over, I was looking at it, and I was like, man, you guys look like you just didn't care, huh? And the guy was like, what do you mean? I was like, well, you got things sticking out right here, you got legs right there, and it's just, yeah, it was just interesting to see the different perspectives from, and ours turned out pretty well, to be honest. For community college and our budget, we did really, really well. So yeah, just to piggyback off what you was talking about. Yeah. So we did a capstone project before we even graduated. Go team.
The community college equivalent of capstone, I guess, except that we're still here, so.
Do we have any other questions? Let's give a big round of applause. Thank you guys so much for coming and speaking to us today. And before the members of the audience leave, we want you to come up and submit a raffle ticket so you can potentially register to win a free 3-credit class. So please come fill out the raffle tickets. And if you're interested in talking to them about joining the launch team, come on up, give them your information, or go to the website for additional information. Thank you so much for coming. We really appreciate it. And thank you guys. This was wonderful. So very interesting. Thank you.